Hello, today we will be looking at Newton's three laws of motion and how they are used in A-level physics. Newton's first law of motion states that objects remain at rest or move with a constant velocity unless there is a resultant force acting on them. We can use this fact to deduce things about objects. If we encounter an object moving at a constant velocity or at rest, we conclude the resultant force acting on it is zero. It's important to note that there may still be individual forces acting on the object, but in this scenario they are balanced and the resultant force is zero. Similarly, if we encounter an object where all the forces acting on it produce a resultant force of zero, we can conclude it will either be at rest or travelling at a constant velocity. Basically, if it's accelerating there's a force, and if it's not accelerating there isn't a force. Newton's second law states that the force acting on an object is proportional to the rate of change of its momentum. This isn't very useful for calculations, so it's easier to express it as an equation. The force is equal to the momentum over time. And given that momentum is just mass times velocity, the force is equal to the mass times the velocity divided by time. Velocity divided by time is acceleration, and from this we get the famous equation, force is equal to the mass of an object times its acceleration, or F equals ma, which essentially sums up the second law. The simple conclusion of the second law is that getting a massive object to accelerate quickly needs a strong force, and if the object is less massive or is not being accelerated as quickly, the force needed decreases. Newton's third law of motion states that every action has an equal and opposite reaction. This means, in practical terms, if I exert a force on something, then it exerts the same force back on me. This doesn't mean we'll accelerate at the same rate though. If I push a 1 kilogram box with a force of 20 newtons, that box is going to start accelerating at 20 meters per second squared. While that's happening, the box is exerting a 20 newton force back on me, but because my mass is quite a bit more than 1 kilogram, I will barely accelerate at all. Newton's third law of motion is also the reason why things like rockets work. The rocket pushes propellant out of its exhaust with a significant force, and the same force acts in the opposite direction on the rocket, pushing it upwards. Now, let's look at a practical example where these laws of motion are used. Let's say I have a rocket which is pointing upwards, and its mass is 100,000 kilograms. Every second, this rocket ejects 2 tons of fuel downwards at 750 meters per second. Also, we're going to assume the rocket's mass stays constant despite the fact it's ejecting fuel, because F equals ma only works on things with constant mass, and we're going to use 10 meters per second squared as our acceleration due to gravity to make things simpler. Now, we want to find the force on the rocket and how fast it's accelerating upwards. So we know that thanks to the third law of motion, whatever force is being applied on the fuel to make it go downwards is going to be the same force that it's applying to the rocket. We can calculate the force using the second law, F equals ma. But wait, we've got mass, but we don't have an acceleration. We've been given mass, velocity, and time. In order to use F equals ma, we need to rearrange it. In this case, switching acceleration for velocity divided by time. Now the equation works. We can calculate force. So we multiply 2000, that's the mass of the fuel in kilograms, not tons, because kilograms are the SI unit, by 750, and divide it all by 1, which of course doesn't change it. We come out with a resulting force of 1.5 million newtons, pushing the rocket upwards. So we can now calculate the acceleration of the rocket, once again using F equals ma. This time, we rearrange for acceleration, as that's what we want to find, and we get acceleration is equal to the force divided by mass. Putting in the force acting on the rocket, 1.5 million newtons, and dividing it by the rocket's mass, 100,000 kilograms, we get an overall acceleration of 15 meters per second squared upwards. But that's not the whole story, because the rocket is also accelerating downwards at 10 meters per second squared due to gravity. The accelerations are subtracted, and we get an overall acceleration of 5 meters per second squared upwards. Now, if you can do that whole problem, which is about as hard as these questions get, you can be fairly confident you understand the laws of motion. Be sure to look at past exam questions of this type if you're unsure. If there's anything about the specific problem you're not sure about, or you think that I got wrong, please leave a comment and I will do my best to explain or correct it. Good luck in your exams, and thanks for watching.